SymPy Stats is a powerful module within the SymPy library that allows symbolic manipulation of probability and statistics in Python. It is particularly useful for modeling random variables, computing probabilities, and performing algebraic analysis of statistical properties. In this video, we will explore its key feature, including defining random variables, calculating probabilities, working with symbolic distribution, and some real-life examples.
Key features of SymPy Stats include defining different types of random variables, computing probabilities symbolically, analyzing statistical properties like expectation and variance, and handling conditional probability. Let's explore these features through some live code. SymPy Stats allows us to define different types of random variables such as normal and exponential distributions. Here, norm is the standard normal variable and ext follows an exponential distribution. These symbolic definitions allow for algebraic probability computations. One major advantage of SymPy Stats is its ability to compute probabilities exactly. Let's calculate the probability that norm is greater than 0. Here, we get half, which is correct, and unlike numerical methods, this gives us an exact symbolic result, making it useful for theoretical analysis. SymPy Stats also allows us to compute key statistical properties like expectation and variance. The expectation of norm is 0, matching the mean of our normal distribution, and the variance is 1, corresponding to the standard deviation squared. Other key features of the module include the moment, entropy, density, and cumulative distribution functions, and many more. Now that we understand the basics, let's apply SymPy Stats to real-world examples. Let's start with a simple probability example, a fair coin toss. We calculate the probability of getting heads and simulate multiple heads. Since this is an unbiased coin, we get probability of both heads and tails as 0.5. Now, let's model rolling a six-sided die, finding the probability of rolling a number greater than 2. We get 2/3, which is correct. For our next example, we know that Bayes' theorem helps update probabilities based on new evidence. Using SymPy Stats, we can calculate the probability of a person actually having a disease given that they tested positive. We get a very small probability, which is a result of the Bayes' theorem. Now, let's focus on a more complex example. Grading students using a normal distribution. If a student If student scores are normally distributed with a mean of 70 and a standard deviation of 10, we can determine how many students fall into each grade category. We assume a class size of 100. This plot shows the expected number of students in each grade category. For a class of 100, most students score around the mean, falling into the B and C category, with fewer students achieving A or F.
In conclusion, SymPy Stats is a powerful tool for symbolic probability and statistical analysis, ideal for theoretical research and mathematical proofs. Whether for the academic study, probabilistic modeling, or symbolic computations, SymPy Stats is a versatile tool in the Python ecosystem. For further exploration, check out our blog as well as the SymPy documentation. Thank you and have a great day.